So,
It's not yours to touch, man.
and we
I
don't,
lost a bunch of things.
okay. It shouldn't be too many. That should be plenty. That should be plenty. So we're starting our penultimate unit in this course. Penultimate, of course, means second to last. Ultimate would be final. So this unit is all about something called equilibria. Sure, yeah, absolutely. Give me a sec. I will. Actually, even better. Thanks, Kirk. I don't know, to be honest.
No, this is perfect.
Maybe the back one. Let's try that. How's that for everybody? All right, look at that. So this unit is about equilibria. Equilibria is plural. What's the singular then of equilibria? Equilibrium. Good. You don't need to write this. Actually, let's write it. In non-sciencey terms, we're not talking about science here, just talking about in your day-to-day life. If you're talking about somebody who has maybe lost his equilibrium, what do we mean by that?
Lost their balance.
Yeah, balance. We use that word in our day-to-day life to talk about things being balanced. All right? No, actually, though that would be nice. Though you will have to balance equations to do these questions, but just as a first step. But this is all based on the idea of balance. And if you think about it, that makes sense because the first half of the word equilibrium is equal, right? So it's the idea of things being equal. Now, what did we talk about at the end of last unit? How did we finish off last unit? It was like a little 3-day barnstorm through the idea of what? Yeah, you had it. Just be louder. Nice and loud.
Rates of reaction.
Oh, that was good. Rates of reactions. Good. So we talked about, don't judge me. I don't trust your smile. So we talked about rates of reactions. How quickly a reaction happens, right? What I want you now to imagine is this. I want you to imagine 2 reactions for me. Let's look at 2 reactions. It is. Okay. Let's look at 2 reactions. The first reaction, I want to look at the synthesis. Actually, no, we'll say this. The combustion of hydrogen. So take a minute and write a balanced chemical equation for me for the combustion of hydrogen. No, don't put your hand up. Take a minute and write a balanced chemical equation for the combustion of hydrogen. If you don't know, talk to the people around you. We collaborate to learn. That's how this works. Good, there we go.
Okay, so you need you just smash them together.
For God's sake, this is not a trick question.
H2 plus O2.
Good. What's it going to give you?
HO2. H2O.
There you go. All right. Come up with that and balance it, please. Good. Now, is that balance? All right. So balance it.
Yeah, good job.
Okay. You guys do a lovely job. When you're finished, would you mind, once you have it? Put it there.
Is that what you do? You put two.
Why are you yelling
just
at me?
you yelled at me.
I didn't yell at you.
Who's
Brian's
yelling?
yelling at me. I didn't yell at you.
Brian, don't yell.
Okay, so
Sarah, stop
Eight.
yelling.
hopefully we're all on roughly the same page.
Two
Good.
plus.
Okay. All right. So when we combust hydrogen, what do we obviously get?
You
What are we
balance.
reacting it with in this
Two.
combustion? With what? Oxygen. Okay. What then is the
That doesn't
product
look
of
like
the
it.
combustion? Hydrogen. Good.
What?
That is correct.
No way.
All right, so we got water. And then to balance it, how many hydrogens do we have to use? Two. How many oxygens do we have to use? Just one. Yeah. And how many waters do we get? Two. Good, okay. That's grade 10 chemistry. And I'm not saying that to be cynical, because sometimes it's hard to remember grade 10 chemistry, but good.
Oh,
Now,
that was the reason. Oh, I keep clicking the eraser. There we
what
go.
would the rate law for this be? What would the rate law for this be? Okay, so rate's going to equal, what do we always start with? Rate equals some constant k. Can we write this underneath?
Mm.
So rate equals, when are we
Woo!
going to have k? Because the rate's going to be some constant k. How do you put an equal sign?
Oh, I know how to do the eraser. There we go.
You got this.
Okay.
Great. I'm just going to train you guys just to do this. Okay, so some constant k, and then we're going to multiply it by what? The concentration of H2. Okay, use square brackets for concentration. So H2 in square brackets. And then to some exponent m, put an m up top. And then multiply by what? Another square brackets with O2. And that's going to be to some exponent n. Yes?
Yep.
Good. Okay. Thank you so much. Now, I want you to look at a second reaction. R is fine. Okay, second reaction. Shh. Shh. Second reaction, decomposition of water. Second reaction I want you to come up with is the decomposition of water. So this time we're going to start with water and we're going to decompose it, break it apart. Good. Yeah, sure, of course you can. Just take your time and be neat, okay? There you go, sir. Thank you.
Decomposition of water.
Why do the H and O have twos beside them?
Okay, that's good. Is that balanced?
No, it's not balanced. Oh, it's not balanced.
I'm hoping to drink it, but I will burn you. I don't want it. Okay, when we decompose water, we get hydrogen gas and oxygen. Now quickly, really quickly, what would the rate equation for this be?
R equals K, some constant H2, some
Good.
concentration of O2.
Okay, I like the rate equals K, and I like that we're doing the concentration to an exponent. But is it H2 and O2 that we're worried about here? Which side of the equation do we look at when we make a rate law? Left. Good. The reagent side. So it's going to be K times what? Times concentration of H2O. To some exponent. Ah, good. Okay. Good job. Now, look here. I want you to look at these two reactions. Zanka, can you zoom out so that we can see them both at once?
Broke.
More ends, because I'm old.
Oh.
The eyes don't work so well. Good. Okay, so there we are. What do you notice about these two reactions?
Oh, that's.
That they
Talk about it. Take a minute. We're going to go somewhere with this. It's going to take a note. Talk to the people next to you. What do you notice about these two reactions? Take a minute.
What do you notice about these two?
Talk to the people next to you.
I gotta catch up.
I'm going to make each table tell me one fact about these two reactions.
Okay, what do we see?
You don't want to be the table that looks stupid, do you? I'm the table that looks stupid most days. Anything about the two reactions. Anything whatsoever. Any factions.
They both involve water. They both.
All right, let's see how we did. Let's see how we did. I'll go first. They're both written in blue. Okay, back table. What do we know about these two reactions? Good. Okay, very good. Okay, nice insight. These two reactions are opposite of one another.
I like the whole.
If you look at the top one, it starts with hydrogen and oxygen, gives you water. If you look at the second one, it starts with water and gives you hydrogen and oxygen. Good, I like that. Secondly, what do we see?
they all have twos in them.
I can look at that. Sure. 2 tends to be the coefficient we use to balance. Now, the deepest insight that works. And listen,
It's
100% true.
chemistry.
That completely fit the criteria of what I asked you to do. Well played. Third table, what do we got? Again, fits the criteria. It's getting less amusing, but okay. Got anything?
We were gonna say that they were the same thing but flipped, but there's water in both of them. So.
Yeah, same thing, but flip, water in both of them. I like that. That's the big takeaway anyway. What about you guys? What do you got?
They became the same reactants and products.
Okay. Good. You
Good.
guys?
No, we're the same.
Okay, I like this. I like this. Even though they're the same reaction but backwards, one of them has a single reactant, the other one has 2 reactants. I like that. Good. Did anyone look at the rate laws themselves?
I did.
Okay, what do we notice about the rate laws?
The rate laws, one has the H2O, 2 has H2O, and combined.
Good. Now listen,
When you're
guys, this is great. Now, we said that how quickly a reaction happens depends on the concentration of its reactants, right? We wrote 2 laws here. Here's what I want you to imagine. Are these both real chemical reactions?
Yes.
So they're both real. So in real life, will both of these happen?
Yeah.
Yes. Now, instinctively, one of these usually happens pretty quickly, and the other one does not happen quickly at all. Just based on your real life experience, or what you've seen or heard or read, does hydrogen react with oxygen to make water quickly, or does water break down into hydrogen gas and oxygen gas quickly? Under normal conditions. Well, let me ask you this. We have water all the time. If I fill this thing up with water, will it be a matter of moments and the room will be full of dangerous hydrogen gas and we'll all have to flee for our lives? No. Thankfully, our water is quite stable. That second reaction absolutely happens. That is a real reaction. And you know we've done it in the lab by speeding it up with electricity, right? But even without electricity, that reaction will occur. But does it occur quickly? No. Let's talk about hydrogen reacting with oxygen. Happens quickly. You did gas testing in grade 9, right? Where you got the test tube and you put the splint in it and it goes pop.
That was fun.
Yeah, remember when chemistry was fun? God, me too. But that reaction, all of that hydrogen becomes water in the blink that sound pop is the time it takes for all of the hydrogen to become water. That's pretty quick, isn't it? Okay, but according to this, If I want the top reaction to go faster, what do I need more of? Hydrogen oxygen. And as we use it up, what happens to that top reaction? It starts to go slower and slower and slower, right? Does that make sense? In the meantime, how do I make the bottom reaction go faster? I need more water around, right? Does that make sense? So here's what I want to get at today. These two reactions are opposite of one another. In other words, as the reaction above makes water, what does the reaction below do? It breaks up water. These reactions both happen.
That's a
Which means-
hydrolysis. No,
Which means, listen, under any normal circumstance, hydrogen is always being made along with oxygen from water. But then, as soon as we make hydrogen and oxygen, what reaction becomes favorable? The top reaction. Are you bearing with me here? So what's then going to happen to that hydrogen and oxygen? They're going to react and become water. Does this make sense? And then once it reacts to become water, what can then happen to that water? It can break down, make hydrogen and oxygen. At which point the hydrogen is available to react with the oxygen and become water. Is this starting to make sense? These two reactions run opposite to each other, and they're both happening all the time. Okay, and I'm going to write that. And so are you. These reactions both occur in nature, and they are opposite one another. So these reactions both occur in nature, and they're opposite of one another. Now, what we're going to do, I want to look, for the sake of giving you the principle of this, at even easier made-up reactions. I want you to imagine a reaction where A turns into B, and I want you to imagine another reaction where B turns into A. Reverses of one another, opposites of one another. Does that make sense? So we're going to look at a second example, a nice, easy example. Doesn't matter what A and B are, we have one reaction that turns A into B, another reaction that turns B into A, right? Yes. Well, with that in mind, the rate of the first one would be some constant K times the concentration of A to some exponent, right? And the rate of the second one would be equal to some constant times the exponent B to some other exponent. Does that make sense?
Yes.
Okay. Now, here's what I want to drive home. We'll call this reaction 1. As reaction 1 begins, what does it produce? It produces B while using up A. Okay. Shh. Now, make these both the same color, otherwise I'll go crazy. So, as reaction 1 happens, it begins to make B, and it's using up A. Can you picture this? That makes sense, right? The first reaction happens by taking A and turning it into B. So we're going to decrease our concentration of A, while the concentration of B goes up. Now, what will that do to the rate of reaction 1? if we're making the concentration of A go down? Good. So reaction 1 goes slower as a result of this, right? So as reaction 1 happens, it slows itself down. Can you picture that? Because as it uses up A, it decreases its own rate and decreases its own rate. But it also is making B. And what is that going to do to reaction 2? Good. So reaction 2 goes faster. Okay, perfect. Except that at the same time, reaction 2 is happening, right? And as reaction 2 speeds up, it produces what? What does the second reaction produce? It produces A while using what? Okay. What will the result of this be then? As the second reaction goes, what does it do to reaction 1? It's producing B, keep in mind, or it's producing A. So it's going to speed up reaction 1. And what will it do to its own reaction? What does it do to reaction 2? Slows it down. Okay. Now, hopefully you see that this then begins a cycle. Because now that reaction 1 is going faster, reaction 1 is going to produce even more B while it uses up even more A, right? And as that happens, what then happens? It slows itself down and it speeds up the other reaction. Can you imagine this? And then, because it's speeding up the second reaction now speeds up and it produces lots of A and uses up lots of B, which then makes the first reaction go faster. And it makes itself go slower. And eventually, if you push and pull and push and pull and push and pull and push and pull, what should happen? I want you to imagine this. Think of it like being on like a teeter-totter type thing, right? As one person pushes up, the other person goes down. And then they push and push and push. Eventually, what should start to happen?
They'll balance out.
Eventually, they should balance out. Eventually, reaction 1 will go at such a speed that it is making B just as quickly as reaction 2 is using B. Does that make sense? So reaction A is going to go, and eventually it'll hit this sweet spot where it's making B at the same speed that the second reaction is using B. Does that kind of make sense? It's going to start as chaos. It'll start with one going faster than the other, and then because it's going really fast, it'll push the other and it'll go faster. And it's going to go back and forth, and eventually it hits this equilibrium point where the reactions are still happening, but the forward reaction is happening at the same speed as the reverse reaction. Now, can somebody think of an analogy for that? Where something is going forward at the same rate that something is going backwards. As you may know, I'm a bit of a health nut. I love to exercise. It's my thing. Some people like to eat, some people like to read, some people like to solve problems or, help people. I like to exercise. It's just me. It's who I am, mind, body, spirit, all that. That's just me. So I like to exercise. And of course, in the summer months, I run. But in the winter months, this isn't true, by the way. I don't even own one. But I like to spend time on a treadmill. And when I get on my treadmill, if I set the speed of the treadmill too fast, what will happen to me? Yeah, specifically, I will be thrown off the back, and presumably somebody will film it and put it on YouTube with some sort of title that starts with epic fail. On the other hand, if I set the treadmill to a slow walk and then got on it and ran at full speed, what would happen to me? Yeah, I'd run right over the front and also have a YouTube video of me starting with epic fail. The idea of a treadmill is it works when you get on it and you move yourself forward at a constant speed, and not just any constant speed, because I could get on my treadmill and try to move forward at this constant speed, and if it's going back at like 20 kilometers an hour, I have a problem, don't I? Not only do I have to go at a constant speed, I have to go at the same speed as the treadmill. And if I do that, if I manage to coordinate myself in such a way, and of course I do, because I'm quite sporty, when I get on my treadmill and I move forward at the exact speed it's moving backwards, if somebody's just standing there looking at me, how do I appear to be moving? I appear to not be moving. I mean, I appear to be flailing all the time. So that wouldn't be much of a departure. But I look as though I'm staying in one place, because I am staying in one place. Even though I'm exerting tons of energy to move forward, at the same time that the treadmill is exerting tons of energy to move backwards. This is why I refuse to use a treadmill, by the way, because it's stupid. Because the idea of getting on something and working my butt off to go nowhere just feels too much like, I don't know, it's so futile. And I get so depressed about it, I'm like, I gotta go eat some bread. But I don't get it. I don't get the possible appeal of that. I don't understand how people do. But that is how reaction equilibria work. When a reaction happens, we get to a point where we look at it and it looks like the reaction has stopped. But in reality, the reaction never stops. What happens is there's two reactions happening at the same time. One going in the forward direction and one going in the reverse direction. And when it appears to stop, what has really happened is that the rate of the forward reaction matches perfectly the rate of the reverse reaction. Does that make sense? So eventually, sorry. Thank you. Now, one of the things to keep in mind is that it's not just chemicals. Things are at equilibrium all the time. We don't necessarily think about it, but things are at equilibrium all the time. Right now, these exhaust fans are running because I run them in here all the time because let's say I hate the environment. I just forget to turn them off. So these exhaust fans are running. They are taking air out of the room. But none of us is suffocating and dying right now from a lack of air. None of us is being asphyxiated. Why? Yeah, because from the bottoms of the doors and from that open door and these windows that are open, air is coming in. And we don't think about it. It's just automatic. We understand that that happens, right? But we understand that when you let nature take its time, it eventually will balance every leaving of something with the coming of something else. The expression is nature abhors a vacuum, right? I recently, I have an air compressor at home. And I always forget until like I hear it sloshing around. You're supposed to, every time you use an air compressor at the end, you should drain it because liquid forms inside. Which you guys totally understand because of PV equals nRT. You know that as you release gas from it, the temperature drops. As the temperature drops, the solubility of water in air drops. And so it condenses and forms liquid water at the bottom of your compressor tank. And you're supposed to empty this out regularly so that the steel walls of your compression tank don't rust, which is good, right? Because then they could burst and that would be bad. So they have a little drainage valve. I always forget to do this. But they're actually quite clever. They intentionally use a nut in the drainage valve that rots out quite quickly. It rusts and rusts away fast so that if you do forget to drain it, instead of your tank corroding, they've designed this bolt as sort of a fail-safe where it doesn't last very long. So I'm in a state now where this bolt has a nice amount of rust caked on it, and every time I run my air compressor, you can hear this hiss of air escaping my air compressor even when nothing's attached to it, because this bolt is now porous and it's letting air out, and so I have to replace it. But, which of course I just haven't done for weeks, because whatever, just run it anyways. But that is nature finding an equilibrium. There's pressure inside, there's lots of air inside, and by nature, it wants to let that out until such time as equilibrium is met. So it will decrease the pressure inside the tank. In so doing, it'll increase marginally the pressure in the room around it, because that air has to go somewhere. But this will keep happening until they balance each other. This balancing act of nature is totally normal, and it's what we expect, right? It's how we walk around every day, right? We apply pressure to the earth, and the whole thing works because the earth also applies pressure back to us, all right? And ask, astronauts living on the International Space Station how easy it is to get around without that equilibrium, how easy it is to work when everything you touch, if I push this that way, it also moves me this way, every single thing you do, right? In a gravity-less environment in space. It becomes very difficult to get work done. Because every movement you make, the opposite movement actually happens, because nature will find equilibrium wherever it has to. And if it doesn't have gravity, if it doesn't have the earth pulling you down to equilibrate against your motions, it will just move you, right? All of which is to say, this happens to chemicals as well. Every reaction has a reverse reaction. Every reaction can be undone. That's one of the things you learn. And I always remember when I was in grade 9 science, hands up if you remember them saying that, the difference between chemical reactions and physical reactions. And they said one of the things about chemical reactions is they're all reversible. Do you remember that? Well, you should. Anyway, you filled it out on a worksheet when you were in grade 9, I promise, because every grade 9 teacher uses the same friggin' worksheets. You get them in yeah, there you go. So listen, I know you know that, but listen, when I was a chemistry student, I remember finding this very confusing, right? What do you mean an explosion is reversible, right? Like if you're telling me that if I take my chemistry textbook and light it on fire because I've just had enough, is that really reversible? And the answer is actually, believe it or not, yes. Now, in practice, are we actually going to reverse the reaction in such a way that we end up with our textbook back? No, we're not. But still, every one of those individual chemical reactions can actually go the other way. But those reactions happen much, 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 much slower. They happen at an infinitesimal rate. It is very unlikely that atmospheric hydrogen and carbon come together and make gasoline, octane. It does happen. It really and truly does randomly happen. It happens so infrequently that the rate of that is really low. So the chemical equilibrium for an explosion is such that when it hits this point, there's very, very, very little octane and lots and lots and lots and lots and lots of water and carbon dioxide. But even that reaction, even you burning gasoline in your car engine is reversible. It's a reaction that goes both ways. And when it reaches equilibrium is when it's finally going at the same speed in both directions. Now, again, for burning gasoline, that only happens once almost all of your gasoline is gone. Once you've used up down to, at this point, we'd be talking individual molecules. Very low reverse reaction rate. That still does happen. If you can picture this, you have to remember how small atoms are and how big we are. But at equilibrium, the rate forward is equal to the rate backwards. At equilibrium, that's a attempted race bracket. Do you want me to try again? That was weak. I'll admit that. Is that better? A little better. And that's it for today's lesson. Tomorrow, now, interestingly, if you'll notice where we've left off, that the rate forward ends up being equal to the rate reverse, I'm setting us up to do what tomorrow? Some math. I'm setting us up to do some math, because we know how to calculate the forward rate of a reaction, don't we? And we know how to calculate the reverse rate of a reaction, don't we? So can I eventually make an equation that will talk about how things appear at equilibrium? Yep. Yeah. And that's what tomorrow is going to be about. So at the end of last unit, we learned about rate laws. Hopefully we learned about them. At least we talked about them. At the beginning of this unit, we're going to talk about equilibrium laws. Hands up if you would say that what I spoke about today makes absolutely no sense to you and you don't get it. Be honest, it's okay. That's how I feel. I'm taking a physics class right now, and that's how I feel most of the time. There you go. Hands up if you say, I kind of get it, but I don't really completely get it. Okay, good. Hands up if you're like, yes, this makes perfect sense and I understand it. Okay, thank you for the feedback. Here's what we're going to do. Tomorrow, we're going to do a little bit of kind of talky talk to work through and see if we understand this a bit better. Today, we've still got some time to work on your papers. Remember, I want your first submission peer edited by Friday. All right, so you got to get moving on that. There'll be late marks for the steps on this. All right. If you do need some kind of extension, don't ask me on Friday. The answer will be no. Talk to me today. Okay. Because if you show up on Friday and say, "Oh, I just couldn't get to it," I'm gonna put my mean teacher hat on and say no. I'm gonna put my make Smithville great again hat on and just refuse. I might get a red make Smithville great again hat. I don't know. So that's one. Secondly, the reach ahead activities for last unit, I'm going to put up today. There's only going to be two of them. One lesson, one lab. This lab will not be a write-up. It'll be an activity that you come in on your own time and do, but there'll be a worksheet to fill out while you're doing it, and that'll be that. So it's not a big time commitment on this one, but it is a really nice, fun, funky lab. It uses some of the equipment. Even if you haven't been doing the rate laws, haven't been doing the reach aheads, I'm sorry, this is actually a really cool lab. It uses some of the probeware, hooks up to the computer, it gives you nice sparkly graphs, and it's colorful, and it's cool. I like this one. So it's a goodie. Third, I marked all of the tests that were done day one. I haven't marked any of them from yesterday yet. I did like a run through of Zabos because I was there, but mostly I haven't got them yet. So far, I'm really pleased with them. Very well done. Still a bunch of people who haven't written. So you'll get them back Friday. That's our timeline. You'll get your test back on Friday. Yeah.
Could we ask Mark what we got?
You could ask. I don't know them and I haven't put them in yet. If I think of it when I get home, I'll put them in which case you'll be able to go on Edge. Oh, you guys can't go on Edge, so you can't yet. Okay, if you can go on Edge, you can go on and see them when I put them in.
Yeah.
There you go. Yes.
Are you still dropping a test mark? Or not this semester?
I don't want to talk about that this semester. I'll come up with something. We're gonna get 5 full tests in this semester, so I will. I just don't know what my format for that will be. If I'm just gonna drop the lowest, or if I'm gonna put something in its place. I'll do something because I believe in that. As somebody who's had a bunch of bad days in his career, I understand what it's like to have a bad day writing a test. So I think that's fair. Yeah.
So I'm writing my test in M6. I write in my M6 or my
Come to me. Come to me. I'm covering 2 M6 this afternoon. I'm gonna move them both to this room, just for simplicity's sake. So yeah, so come here.
Will my test be here?
Yeah.
Okay.
Yeah, I've got all your tests. So reach ahead activities will go online. Again, this unit's nice. There's only 2 of them. Paper, we want our first submission for Friday. Again, don't be shy to ask for some feedback before then. A bunch of you have, which is great. And again, I want you to digitally share it with your peers. Did everyone see yesterday's instructions where I put the rubric by which I'm marking it online?
Yeah.
Everyone saw that?
Yeah.
Maybe I'll stick it up here just to make sure. So this is the rubric by which I'm marking it. So when you go to evaluate your peers, by all means, listen, by all means, make simple grammatical corrections. That's great. If I don't have to, because you do with each other, fantastic. By all means, if there's spelling mistakes, say, hey, you've spelt this wrong, you bet. But what I'm really looking for you for is to read your peers' paper and to look at it based on these criteria. I'm not looking for you to edit it the way I do by putting hours into it, because I know that's not realistic. But what I am looking for is you should have some kind of meaningful comment about each of these categories. You should have something meaningful to say about your peer's introduction, about his or her abstract, about her ability to demonstrate her understanding. You could maybe, and that's a big one too, like, does it sound like you know what you're talking about? Or does it sound like you're full of crap? Listen, it doesn't go away. You see stuff published by people all the time. I see stuff written in like district school, like stuff that comes out on letterhead. And you read it and you go, this person sounds like he or she has no idea what any of this means. You don't want to be the person who writes that way. It is much better to write a paper saying, I don't really understand this element of it, or just not talk about it, than to put a bunch of stuff in there that you clearly don't understand. That's a good guide to us as writers. Don't try to discuss something you don't get. It's transparent, all right? A reader knows when you're talking about something that's over your head. That's obvious. Better not to talk about it, or better yet, come talk to me, talk to your peers, read the textbook, do some research, figure it out, and then write about it. You cannot write knowledgeably or intelligibly about something you don't understand. So don't try. I would much rather your paper be lacking some information, because I can say, hey, you got to put this in here, than read a page of gobbledygook of you copying and pasting definitions from like an inappropriate source and then changing the odd word and thinking it's going to get by me, because it's not. And I may get to the point where I'm too lazy to call you on it and I just give you a bad mark. And okay, whatever. But that's not a win for either of us, really, is it? So just take the time and make sure that you understand what you're talking about when you're writing. And then when you're reading your peers, call them out on things. Like if you say, you know what? I don't get this and I'm not sure you get this. That's an insult. You're not saying that to hurt somebody's feelings. Let's work through and make sure they demonstrate understanding throughout. Results. That should be straightforward. Have they put their results in there? Okay, good. Boom, level 4. Let's move on. And then discussion. Does it seem like they've written enough? Does what they write make sense? Is there something that you put in your discussion that they didn't think to talk about? Mention that. Hey, I talked about this. This is a collaborative environment. We're working with one another. I don't want you to give your paper to somebody else just so they can copy it. But should you say, hey, one of the things I thought about in my paper was this? Totally cool. And then references and style and formatting. I put a link up on that earlier, how to cite. I would definitely recommend using Word Citation Manager. That's what my video instructions are for, because it's easy and it works. If you are some kind of masochist and you're like, no, I really want to do it by hand, go nuts. And I'll be happy to sit down with you one-on-one and show you how to cite things by hand. But in 2016, people don't cite things by hand because it's stupid. When I was in university, you would spend hours working on your citations. How dumb is that? When you think of just the hours that went into making sure there's a comma here, and that's a semicolon, and this is italicized, and that starts with a capital, and there's one space here, and then you'd accidentally put 2 spaces there, and your prof would like take all the marks for citations off of your paper, and you'd be like, I lost 30% because I didn't put it. It's stupid. It's a waste of everybody's time. In 2016, you can say, hey, Microsoft, here are my references, cite it, and it does it, and it does a beautiful job. So use that feature. It's a lovely one. A word to the warning, their APA actually isn't the most up to date. So if you have a really stickler of a university professor, you'll actually have to go in and make a couple of tweaks to each citation. I am not a super stickler, and I'm really happy with what Microsoft spits out for us. I think that's perfectly reasonable. Okay, any questions about that? Prove it? I don't know what that means. Oh, okay.
You're just talking to yourself.
I respect that.